So welcome to this second lecture. First lecture we have seen basically revision of our undergraduate course, and we solved some problems, and I told you about the different ways of characterizing reactors in general, and what are the 5 things that we need to specify for specifying any reactor. You think about any reactor, you will have to specify these 5 things, and only these 5 things if you specify, then only your reactor description would be complete, and then only you can design the reactor. So what we are going to do now is go forward in the course. This is the second part of the course we are on, real life reactors. We are looking at some design aspects. We are going to look at simple reactors, plug flow, well mixed, batch reactor. We are going to look at multiple steady states. We are going to look at reactor stability of different reactors. So what we are going to look at first is the first part of the lecture. We are going to look at design aspect. That's what the first part is, part 1 of this real life reactors part of the course. Just to quickly revise, relate conversion to time for a batch reactor, PFR and CSTR for a homogeneous liquid phase, let's say second order reaction. Okay. Second thing is, what are the different aspects that characterize reactors? 5 things that I told you about. Revise, right? If you don't recall, it's okay, go back and study the lecture and make your own notes. Okay. So here is a real life problem. Imagine that company wants to make a product P. Let's say molecular weight of P is 150 from a raw material A by a liquid phase homogeneously catalyzed reaction, elementary reaction A going to P. So when we say elementary reaction A going to P, what do we mean? When we say elementary reaction, what do we mean? What we mean is that rate, let's write rate here. The rate, it's a first order reaction, elementary reaction. Rate of reaction of A is Kc, or minus Re, if you like, is Kc. Okay. So company wants to make 12,000 tons per annum of this product P. Reaction is known to be exothermic with a heat of reaction of minus 30 kilocalories per gram mole. Reaction is exothermic. Heat of reaction is minus 30 kilocalories per gram mole. So perhaps R&D has studied this reaction. R&D department has studied this reaction in a laboratory 100 ml reactor, starting concentration of 2 kilomoles per meter cube of A along with the catalyst, solvent, whatever you want, whatever is there. And imagine that you have been assigned the task of designing a reactor for the company that will operate with 98% conversion of A. So obviously you will go to R&D, you will look at their data, and this is the data that R&D has given you. Let's say after 20 minutes at 120 degrees centigrade when they conducted the reaction, after 20 minutes conversion is 4%, 40 minutes 7.5%, 60 minutes 11%, and so on and so forth. They also conducted the reaction at 150 degrees centigrade. It took in 20 minutes the conversion is 13%, 40 minutes it is 24.5%, 60 minutes it is 34.5%, and so on and so forth. So this is the data that is given to you, made from the R&D, available. What you have to do? You have to design a reactor. You have to design a reactor. Okay. What does that reactor have to do? It has to ensure that 98% A gets converted, and it has to ensure that you will make 12,000 tons per annum. If any of these are not met, if 12,000 tons per annum or 98% is not met, obviously company is not going to accept your reactor design. Okay, both these. And important thing, you have to do it safely as well. You don't create explosion, this, that, other. Okay, so you have to design a reactor. Okay, solve this problem yourself. Let's see what you come up with. Okay. You might want to write some steps first. that I will do this is my step 1, step 2, step 3. And once you write all these steps, then you might want to do some calculations. And what you should come out with is reactor design, meaning volume is only one part of the reactor design. When you say design, volume is one aspect. It's an exothermic reaction. Second thing you have to say is how you are going to remove heat or operate adiabatically. Third thing you will need is not just reactor, but how in general, what is a process flow diagram, how the whole process is going to look like of operating the reactor, piping and instrumentation diagram. This will complete how are you going to control flow, how are you going to control level if you want to control, temperature if you want to control, pressure if you want to control, how are all these things going to be done, piping, 1-inch pipe, 2-inch pipe, 4-inch pipe, 12-inch pipe, instrumentation and control, they are related. This is what we mean by reactor design. Not just finding volume. This is what you've done in your undergraduate course. You have just found out volume. Residence time multiplied by flow rate, you just found out volume. But that's not all. Okay. So at least find volume now. So pause the video, do this for yourself. Some of you may be stuck at first place. We haven't been told what reactor to design. We haven't been told whether it's a batch reactor, whether it's a continuous reactor, whether it is well mixed or whether it is plug flow. We have not been told anything. Then you will say, how do I design if I am not told these things? But treat this like a real life problem. That's what we mean. It is a real life reactor. This is a real life problem. It is a real life problem. You imagine that you are working in a company that wants to make 12,000 tons per annum, 98% conversion, initial concentration 2 kilomole per meter cube, heat of reaction 30 kilocalories per gram. This is the data. This is what a real life reactor is. It's a real life scenario. You have to decide everything that you want, but you have to ensure 12,000 tons per annum. You have to ensure conversion. You have to ensure safety. You have to ensure that it is economic. Oops. You have to ensure that it is safe. You have to ensure that it is an economic design. Economics of the process work out. This is what you have to ensure. This is real life. That is why I call this part of the section of this course, as real life reactors. Real life reactors. Pause the video, do it for yourself. Here is one possibility. First of all, to do any calculations, we will need kinetics. Right? We need kinetics. So, if I need kinetics, do I have data of concentration versus time? Yes. Batch reactor. This is R&D batch reactor. We could do a integral method, we could do a differential method. Do this for yourself. Integral method, if you do ln 1 minus x versus time, if you plot, you will get a straight line at 120 degrees centigrade at 150 degrees centigrade. This is the data at 120 degrees centigrade. This is the data at 150 degrees centigrade. Okay. So you will get rate constant as a slope 0.001991, almost 0.002, and 0.00678, almost 0.0068 minute inverse at 1. So if you use these two data, plot ln k versus 1 by t, right? ln k versus 1 by t if you plot. Remember what k is? K is k0 exponent of minus e by rt. So if you plot ln k would be ln k0 minus e by r 1 by t. So if you plot ln k versus 1 by t, ln k versus 1 by t, these two data sets if you plot, slope would be minus e by r, and you can find out the energy of activation from there. Okay, and then you can find out k0 as well. Okay, so now you got the kinetics. So these are the kinetics. You got these kinetics now. Design. Pause this video. Do this for yourself based on this. Next question you will ask is whether I should conduct at 120 degrees centigrade or whether I should conduct the reaction at 150 degrees centigrade. Choice is yours. You are the designer of the reactor. That's why I call this as a real life reactor. These are real life reactors. This is the second part of the course. Do this for yourself. I'm just going to give you some thoughts. Okay, pause the video, do it for yourself. Okay, suppose we use a well mixed reactor, right? Then we've got our design equation, right? This is what we had derived already. If I conduct reaction at 120 degrees centigrade, so K I can calculate, I know. XA I know, 98% reaction, right? We can calculate tau. So if I say reaction temperature is 120 degrees centigrade, I can calculate K, I can calculate tau. If I say reaction temperature is 150 degrees centigrade, I can calculate K, I can calculate tau. Suppose I don't want to do reaction at 120 degrees centigrade. Nobody has forced me to do at 120 degrees centigrade. In the laboratory that they have studied doesn't mean we'll have to operate it in the plant at 120 degrees centigrade. Maybe we'll do reaction at 90 degrees centigrade. We'll get K, we'll get corresponding tau. Because we know E by R now, we know energy of activation. So we can calculate K at any temperature. Why 150? R&D has studied up to 150. Doesn't matter, that doesn't mean that we have to stick to 150 in the plant. Maybe we'll do at 180, maybe we'll do at 200, maybe we'll do at 250. Each of these cases, I will have a different value of K. Correspondingly, using this performance equation, we can get tau. How will I get volume? From tau, how do you get volume? To get volume, you will need flow rate. How will you get volume? To get volume, you will need flow rate. So what is the flow rate now? Second important point. So first important point is what is the flow rate? Second important point is it is to be operated at steady state. Third important point is it is well mixed. It is well mixed. Right? Think about a process flow sheet. Think about process flow diagram. Pause the video, think about it yourself. Think about piping and instrumentation diagram. Think about it for yourself. I'm just pause the video, do it for yourself. Doesn't matter if you are right or wrong. Here's one possible flow sheet. There could be a storage tank in which we will take A, we will put catalyst, solvent, whatever is there, steady state, continuous. Okay. So we'll have to pump this into our reactor. This is going to be our well mixed reactor. We'll take it out. If I have to maintain isothermal conditions, what do I need? I need to remove heat from the jacket. So there would be a jacket. There would be coolant. Cooling water, let's say out. Cooling water in. What else? What else do we need? We need agitation. We need to ensure well mixed. We need agitation. So we need motor. So suppose I want to do reaction at 200 degrees centigrade. And let's say this is stored at atmospheric condition, 30 degrees centigrade. How will it go to 200 degrees centigrade? Well, I may need a heater in between. So product is going to come out at 200 degrees centigrade. Can I sell product at 200 degrees centigrade? No, I will need to cool. Then I will have to separate out, maybe A and P to be separated, maybe distillation column, whatever. This is what I will need to do. Now this is my reactor process flow diagram. So when we say design the reactor, I have to design not just the volume, not just the volume. I have to find pump, I have to find storage tank, I have to find exchanger, I have to specify motor, I have to specify volume of the reactor, I have to specify jacket, how much cooling water is required, how I will cool, what is the separation strategy. All this is a part of now our reactor design. See the difference between your undergraduate course. Your undergraduate course stopped here. This is where UG course stopped. This is now real life. This is now real life. This is what we need to do for our design. Okay. Here are, try this yourself. Try specifying all these things yourself. Pause the video. Here are some thoughts. Okay. How will the reactor look like in the plant? What other hardware or equipment is required? How will it be implemented? What temperature you will operate. Here are some thoughts. So assume that 2 kilowatts per meter cube of agitator power is required to ensure well mixed reactor. So I'm going to require 2 kilowatts of power per unit volume. So if reactor is 10 meter cube, I will require 20 kilowatts of motor. If reactor is 100 meter cube, I will require 200 kilowatts of motor. Okay. Use a standard agitated tank design. Height to tank diameter ratio is 1.5. Impeller diameter to tank diameter ratio is 0.4. 2 pitch blade turbines. Power number is 2.5. Here is what I mean. So this is my tank, agitated tank. I will use 2 pitch blade turbines. D is the diameter of the impeller, T is the tank diameter, H is the liquid height. Recall how power number and power are related. Power is NP rho n cube d raised to 5 for one impeller and for second impeller as well. And so it will be 2 times this number, 2 impellers, 2 pitch blade turbines. Jacket is for cooling water to maintain isothermal conditions. Okay. Some properties are given 900 and 6.6 and so on and so forth. Prandtl number you can calculate. Typical costs. Each heat exchanger costs about 1 lakh rupees per meter square. Reactor costs about 1 lakh rupees per meter cube. Cost of pump is 10,000 rupees per kilowatt. For 1 kilowatt pump. Cost of electricity is rupees 10 per kilowatt hour. Annualized cost is 20% of the fixed cost plus operating cost. Now calculate. What I would suggest is you use an Excel, use a spreadsheet. Do all these calculations in a spreadsheet. Take different temperatures, say 150, 150, 200. Do all these calculations. What flow rate do we need? I'll just tell you one calculation, flow rate. So how much P we want to make? 20,000 tons per annum. 20,000 tons per annum. That's our objective. 20,000 tons per annum. Oh, sorry, 12,000 tons per annum. Oops, sorry. Oops. 12,000 tons per annum. Now, if I want to make 12,000 tons per annum, how much A I have to feed? 98% is converted, so that means 12,000 divided by 0.98. So many tons per annum is required. If it's a continuous process, per hour if you calculate, 8,000 hours are operating in a year, this will be to 8,000. That is the rate. So tons per hour, into 1,000, that will give you kg per hour. Kg per hour of A. What is the molecular weight? 150. That means so many kilomole per hour. 150 is the molecular weight. Just recall. Oops. 150 is the molecular weight. What is the concentration? Inlet concentration is 2 kilomoles per meter cube. Ca in is 2 kilomoles per meter cube. So what is the flow rate required? Flow rate required would be 12,000 into 1,000 divided by 8,000, 0.98, 150 and 2. That means so many meter cube per hour. So what we have got now? We have got flow rate, we have got inlet concentration 2 kilomoles per meter cube, and we have got outlet concentration 98% has reacted. 2% of 2 kilomole per meter cube is remaining. 0.04 kilomoles per meter cube is remaining. Now take different temperatures, calculate the rate constant, calculate the time required or residence time required, calculate the volume required, calculate the agitator power, calculate the impeller diameter, calculate the vessel diameter, calculate the heat transfer, and so on. Then you have everything. Calculate the heater, calculate the heater, we have, calculate the cooler, everything now you can calculate. Okay. Do this. So do it for a PFR now. Again, what strategy would we want? You would want a storage tank, you would want a pump, you would want an exchanger, you would have our flow reactor, we would have our cooler, and we would have our A and P separation. It can go to distillation column, crystallizer, whatever is the separation strategy. Okay. Maybe we have cooling water here to maintain isothermal conditions. Okay. Now again, flow rate is the same as last time, CA in is the same as last time, or our previous case, or well mixed case, CA out is the same. So this is 2, this is 0.04, and this is whatever we had calculated, meter cube per hour, kilomoles per meter cube. Again, take different temperatures. Suppose I want to do this at 120, suppose I want to do this at 150, suppose I want to do it at 200. Calculate the K, use the design equation, because K will depend on that. Then you will get the residence time. Flow rate, you know, you will get the volume. Calculate the exchanger, calculate the cooler, calculate the pump, calculate the pipe size, pressure drop, everything you can calculate. Do this for yourself. Use a spreadsheet. Okay. Use a spreadsheet. I will rub out some of these things so that you can see what I have written. First thing is what temperature. Let's take different temperatures. Let's not be biased by what experiments have been done in the laboratory. Experiments have been done at 120 and 150. Doesn't mean we have to design plant reactor also at 120 or 150. Heat transfer is very different in a plant and heat transfer is very different in a lab. It's not enough to determine residence time. No. How will the reactor look like? So we've done that. Hardware equipment, we've done all that. So find out all the things that you can. So you see now, you require information. What you require is not just your CRE codes, not just residence time. You need pumps, you need piping, you need instrumentation, you need heat transfer. Information or knowledge about all these things are required. That's what makes the reactor design complete. That's why we call it as a real life reactor. Okay. So do all these things for yourself. Complete this exercise for yourself. Suppose, right, so assume some considerations. Assume that to get to the plug flow, we need a Reynolds number of 5000. That means in this reactor, where did that reactor go? Yeah, here. Oh, I have just rubbed it out, but that's okay. In the reactor, you need a, so in this tube, you need a residence time of, you need a Reynolds number of 5000 here. So operating conditions, all these things are same. All these things are same. Right? Calculate the costs at different temperatures. Use an Excel. Batch reactor. So if I say batch reactor, I will get, if I take different temperatures, let's say 120, 150, 180, 200, 220, 250. I can calculate rate constant. I can calculate that batch time. How do I calculate volume? How do I calculate volume? From how do you get volume? So you say we know now it is going to operate at 8000 hours. So if a batch time, suppose our batch time is, let's say 8 hours. That means within 1 year we can do 1000 batches If you are going to do 1000 batches within 1 year, that means per batch we need 12 tons of tea. Do you agree? If I need per batch, I need 12 tons. That means this reactor, batch reactor, has to contain 12 tons of tea. Correct? So 12 tons means 12,000 kgs of tea. How much of A would be there? Divided by 0.98. 98% is reacting. Divided by 150, so many kilomoles, divided by initial concentration. These many kilomoles or these many meter cube of liquid would be there. Provided if the batch time is 8 hours, then I can do 1000 batches. So that will give me volume of the reactor. But if batch time is 8 hours, does it mean that this T is 8 hours? Is this the same as batch time? No. Because in a batch reactor, we have to do different activities. Recall, we have to do different activities. We have to fill the reactor. Right? Filling the reactor will be based on, so if I have to draw a flow sheet now, again batch reactor flow sheet will look something like this. Something like this. Only thing is now you have to add it. It has to enter, and then you will keep it there for some time and then take it out. So you are going to need time for filling, adding catalyst. Then you have to heat up to reaction temperature. So you have fed at 30 degrees centigrade. Suppose you want to do reaction at 170 degrees centigrade, you have to heat to 170 degrees centigrade. Unsteady state heat transfer. Then you have to do reaction. You have to remove heat during that reaction. Then you have to cool. Maybe reaction is over at 170 degrees centigrade. You have to do distillation now at 100 degrees centigrade. So you have to cool. Discharge to another vessel. Maybe cleaning. All these things take time. What you have calculated from here, is only this time. This is the only reaction time. That's what you did in your undergraduate course, and now you are saying that several things are required. Based on your other courses: fluid flow, pump sizing, heat transfer, pumps, vessels, piping, cleaning, filtration, whatever separation is required, right? Unit operations. This is what your UG course told you. Now this is all that is required in a real life. Your batch time is different. These are not the same, because you require additional time for heating, cooling. Okay? Here are some. Do this for yourself. Go forward. Design. Here are some data. You can again say 2 kilowatt per meter cube of power is required to ensure well mixed. Standard agitator tank design, H by T 1.5, D by T 0.4, 2 pitch blade turbines, power number 0.5, use jacket for heating, cooling, 8,000 hours. All the things you can assume same. Cost you can assume same. Right? Cost you can assume same. Use spreadsheet to do calculations. Design a batch reactor at different temperatures. I'm going to show you some Excel sheets, parts of the Excel sheets, but you do it for yourself. You do it for yourself. Here is what you might get. If you take a well mixed reactor, operate at 125, 150, 175, 200, 250 and so on, which means your rate constant is essentially changed. What happens because of this rate constant change? Tau changes, residence time changes, residence time reduces. You see, 19,000 minutes versus 5 minutes. Correspondingly, you can calculate volume. 1684 meter cube, 1684 meter cube versus 0.4 meter cube. Now this, if I have to convert it into volume, if this volume I have to convert, I have to have some head space, so this becomes 2000 meter cube. Some liquid level, some space above the liquid level, that's called as head space. For this 2000 meter cube, I can calculate tank size, I can calculate tank diameter, I can calculate the heat transfer area, I can calculate the power required, motor power 2 times the volume, 2 kilowatt per meter cube, right? In terms of watts. Speed of agitation, heat transfer coefficient we can calculate from the speed, heat generation we can calculate, coolant temperature, area required, and we can now check whether the area required for heat transfer, whether the area available is more than the area required for heat transfer. You see, area available for heat transfer is 222 meter square, area required for cooling is only, for maintaining isothermal condition, is only 9 meter square. Look at some other extreme. If I operate reactor at 500 degrees centigrade, this is the rate constant, 9.7 per minute. I have only I require only 0.4 meter cube, but I have only 0.9 meter square area available, but I require 1.3 meter square to remove heat. Obviously, the heat removal area is insufficient from what is available. You study this in a lot more detail, plot all these parameters, right? You can convert all these to cost. What is the area required? Cooler, heater, convert all that to cost, reactor cost plus exchanger cost. Calculate. You may or may not get exact same values depending on how you have assumed heat transfer coefficient and so on and so forth. But this is what you will find. As the temperature goes up, cost goes down. Reactor volume goes down because rate is faster and faster. But you see, your preheater area required goes up, your cooler goes up, your area required required to maintain isothermal conditions may not be enough. All these considerations start coming into picture. Do this yourself. That is the depth to which you have to design a reactor in a real life. Understand the difference between what we have been doing in our undergraduate course. We have only been finding residence time, we have only been finding volume, and here we are, volume and residence time are only small parts of the whole reactor picture. We need to convert to cost, exchangers, agitators, everything you need. This is why it is called as real life reactors. Okay. Let's go forward. If you think about a plug flow reactor, let's say we take different temperatures, different rate constant correspondingly, residence time will come down, rate constant is increasing, reactor volume will come down, rate constant is increasing. Okay. Now what do we need? We need 5000 Reynolds number. To get to this volume, and I know the flow rate, I can decide what is my reactor diameter to get to this Reynolds number. I know the volume, I know the reactor diameter. Can we not find length? You will find that if you are doing 125 degrees centigrade reaction, you will require 40 kilometers of reactor. 40 kilometers of reactor. Let's go to higher and higher temperatures. Now reactor length comes down, maybe 86 meters, maybe 38 meters, maybe 19 meters, maybe 10 meters. Heat transfer area we can calculate. Heat generation rate we can calculate. Area required for heat transfer we can calculate to maintain isothermal condition. Now you see heat transfer area available is 8,200 meters square. What is required is only 19. Easily satisfied. Somewhere here heat transfer area available is 4 meters square. What you require is 4.5 meters square. Obviously insufficient heat transfer area. Feed preheater, you can do calculations. Out cooler, you can do calculations. All costs you can calculate. You will find that as you go up on temperature or go up on the rate constant, your cost is going to become less and less. Here your exchanger costs are becoming more. That's why it again increases. Okay. Do this for yourself. Understand all these, calculate for yourself all these things. Only then your real life reactor is designed. Only when you address all these aspects. That's when your actual reactor is designed, not when you find the residence time. Go ahead, do for batch as well. Whatever we have studied for well mix, whatever calculations you have done for well mix plug flow, do the same now for batch reactor. Do these calculations. Here are some calculations. So when you start changing rate constant, your reaction time will come down. Correspondingly, if I say 30 meter cube reactor I will take, corresponding to the number of batches, we can calculate how many reactors we would need. So if I say 30 meter cube, I will require 8 reactors. If I take 30 meter cube as a standard reactor size, I will require 5 reactors at this temperature. I will require 4 reactors at this temperature. I will require 3 at these temperatures. Obviously, because number of reactors cannot be a fraction, so it has to be 3. And then further, again it has to be 4, because now it's just a fraction, so we have to just round it up. Why? Because higher and higher temperatures you go, your heating time will go up. You see, your reaction time is 26 hours here, heating time is 3.5 hours, cooling time is 3.5 hours, charging discharging is 1.92 hours, your batch time is 35 hours. 26 hours is the reaction time, batch time is 35 hours. Look at this extreme, your batch time is 0.01 hours, heating time is 6 hours, cooling time is 7 hours, total batch time is 16 hours. You see how all these considerations start coming into picture. Look at this reaction time, what you calculated in your undergraduate course, and now batch time. Reaction time, batch time, reaction time, batch time. Okay. Calculate the cost of electricity, cost of power, and so on and so forth. Now, so come up to this point, pause the video, do the calculations for yourself. That's why even if the lecture is 1 hour, you may take several hours for doing all these calculations. You may take 5, 6, 7, 8, 10 hours. Don't give up. Do all these calculations yourself. Don't just look at the lecture. Unless you calculate, then only you will understand all these things. So lecture is 1 hour, you may take 6 hours to do all these calculations. That's why lectures are not going to be for 45 hours. Lectures may be for maybe 15 hours, 20 hours, recorded lectures. Okay, plus we'll have some online lectures. So do these calculations for yourself. Now I would like you to compare batch, well mixed, plug flow. Do that comparison for yourselves and tell me which kind of reactor would you choose for what kind of temperature or what kind of rate constant. I would like you to think in terms of two aspects. One aspect is the cost. Second aspect is what is the productivity, meaning how many kgs of P we have made per unit reactor volume per unit time, rate if you like, volume productivity. So do these calculations, compare for yourselves. Here is some comparison. These are the two considerations on which I would like you to compare. Productivity, how many kgs of P we have made per unit reactor volume per unit time, and what is the annual cost? Lakhs, so many lakhs of rupees you have to spend in terms of operating cost, in terms of expenditure on capital cost, fixed cost. Compare on these two bases the three types of reactors: batch, well mixed, CSTR. Batch, well mixed, and plug flow. Here is what you will find. Let's just look at this right hand side graph, cost. So if your rate constant is low, obviously plug flow is any day better. So this is for plug flow, this is for batch, and this is for well mixed reactor. In terms of productivity, plug flow will have highest productivity, followed by batch, followed by well mixed reactor. Obviously, these are all obvious things. Look at this. What will you choose? Which one will you choose for what case? Now, if you look at this cost, let's say, obviously you will say, I will choose plug flow all the time. Is that right? What is not captured in the cost and productivity? Look at this low rate constant, low temperature. Look at this data. Plug flow, low rate constant. Look at this situation. When rate constant is low, I will have 40 kilometers of reactor length. Overall volume is less, but can I manage 40 kilometers? No. I would rather have 30 meter cube 8 vessels, or 30 meter cube 5 vessels, or 30 meter cube 4 vessels, rather than having 40 kilometers or 14 kilometers or 6 kilometer long reactor. So although plug flow is having less cost and better productivity, we will still choose batch. Productivity is similar, but convenience. Whereas if you go to higher and higher rate constants, obviously plug flow is much cheaper. I can easily have a plug flow reactor with a 10 meter length, 19 meter length, 38 meter length, 86 meter length, 200 meter length, 380 meter length, easily possible. Whereas batch reactor, we will require 30 meter cube 3 reactors, 30 meter cube 3 reactors, 30 meter cube 4 reactors, 4 reactors. Right? This is easily possible. Well mixed. For these high temperatures, I require how much volume? 36, 20, 11, 4, 2, 1, 1. Right? As higher and higher temperatures you go, obviously cost becomes a consideration, but plug flow becomes so much more convenient. So we can think about two regimes in this case, two dividing lines if you like around this. Here it's a matter of convenience. I will choose batch because then the plug flow lengths become very large. 0.1 rate constant, see where it is coming, 0.1 rate constant. It is coming here. So this is batch plug flow reactor. 0.1 rate constant. It is coming here. Look at this side. Plug flow reactor length is 1 kilometer, 2.7 kilometers, 6 kilometers, 14 kilometers, 40 kilometers. Whereas on this side, 600 meters, 380 meters, 221 meters, 86 meters. So I can define two regimes. One is this regime where rate constant is very slow, very low. I require plug flow is inconvenient. Whereas at high rate constant, plug flow is very convenient. For low rate constants, batch reactor is very convenient. Look at this. 30 meter cube, 5 reactors. 30 meter cube, 4 reactors. This is my dividing line. Whereas at high rate constants, I require 30 meter cube, 4 reactors. So much volume is required, so much cost is required as compared to plug flow, which is very convenient. Well mixed, somewhere in between. This is our dividing line. Somewhere here, I require huge volumes. Somewhere here, well, this is manageable. 2 meter cube reactor, 1 meter cube reactor, 4 meter cube reactor. Right? Both plug flow and well mixed become convenient here at high rate constants. So we can think about a reactor selection decision tree. If our rate constant is very small, slow reactions, which means reaction take hours to complete, then batch is convenient. Plug flow is not convenient because I need kilometers of length. I can do batch or I can do well mixed reactors in series. Well mixed CSTRs in series. If reactions are fast, we can think of plug flow reactor or we can think of single well mixed reactor. Both become manageable. Batch does not become manageable because if reaction is fast, filling, heating, discharging takes so much more time that volume productivity is lost. Batch reactor, volume productivity is lost. Now all the reactor time, reaction time is only seconds and minutes. Reaction time here is 0.01 minute hours, whereas heating time, cooling time 6 hours, 7 hours, so on. Okay? Try to understand this selection tree based on these tables. Now you see how real life reactor decisions are made and what you have learnt in your undergraduate course. First order reaction, plug flow. Is that reality? No, it's not reality. It's not reality. Not at all reality. Okay. So this is what we mean by real life reactors. These considerations have to be made in a real life reactor. Heat transfer, mass transfer, fluid flow, mixing, heating, cooling, charging, discharging, pumping, piping, controls. Whereas in your undergraduate course, what have you learned? First order reaction, plug flow is the best. No, not correct. If our rates are slow, rate constants are small, plug flow will require kilometers of length, whereas a batch would become so much more convenient, or well mixed reactors in series, continuous well mixed reactors in series would become so much more convenient. They will behave like plug flow, but a kilometer length, 100 kilometer pipeline reactor, plug flow reactor, just can't manage. Whereas fast reactions, I can do it in a plug flow reactor. These are the different considerations that come into play when we start dealing with real life reactors. That's why the first part of this course is called as real life reactors. Just to tell you additional considerations that come into picture. Okay. So we'll stop here for this lecture. Do all these calculations yourselves. Make sure that you are able to understand or able to appreciate all the important concepts that are involved, all the important decisions that one has to make, and based on that we will think about plug flow or well mixed or CSTR. Okay. So this lecture ends here. We will take it forward some more considerations, especially now for adiabatic reactions as we go along. Okay, let's stop here.